Welcome to another episode of You and Me and Multiple Sclerosis. My name is Pam, and I've been living with multiple sclerosis for over 37 years. And I have done videos, which you may have watched, on what's exciting on the horizon for multiple sclerosis treatment and even cure. So I've talked about BTKI, the BTK inhibitors, for possible cure of multiple sclerosis, and I've talked about Epstein-Barr virus as a possible cause of multiple sclerosis, and those are pretty exciting advances, I think. But at the same time, I don't really like to put all my eggs in one basket, so I've still been out looking around to see what else is going on in the MS research field. And recently, I came across something obscure. I had not heard about it before. And I don't know whether you have. I'd be interested to know. But this is work that's being done out of the University of Saskatchewan in Canada. And Canada, as you may know if you watched my video on where in the world MS is found, you may know that Canada is the place in the world, the country in the world with the most multiple sclerosis. I saw a statistic that 1 out of every 12 people is diagnosed with MS every day in Canada. And that was really kind of astonishing to me because that's a lot higher of a percentage than the number of people who are killed in fatal automobile accidents in Canada in any given year. So, that got my attention. But the University of Saskatchewan in Saskatoon is working on this new, well, it's not even really new, something that they've been actually working on for quite some time. And the professor that they have recruited to be their first ever head of their neurology department, a man named Dr. Michael Levin, has been leading a lot of interesting work on the idea that there is actually a protein that causes the problems of neurodegeneration. With all the research that I've come across now, I am convinced that Gavin Giovannoni is correct when he talks about smoldering MS and that all MS is progressive MS because there's something going on below the radar. So whether your brain scans show new lesions or whatever, even if you aren't having actual symptoms or relapses, you've still got smoldering MS going on at the cellular level. And so what I was interested in this research that I'll be sharing with you in a minute is the fact that it does actually look at MS that's kind of smoldering beneath the surface and postulating a mechanism that I had not heard about before. And what I'm going to do is play part of an interview with Dr. Levin that was held fairly recently in September of 2021. And he talks about his research in a lot of detail so that you'll understand not only what the research is about, but all of the components of it and why it takes the time it takes to do this kind of research. And I thought it was quite fascinating. So I think that you will enjoy listening to this as well. Let's go ahead and listen to the excerpt of the interview, bearing in mind that I am going to link the whole interview down below in the description so that you can listen to the whole thing if you would like to.
The late 80s, early 90s, there were no MS drugs approved to treat MS. And now we have more than a dozen, and they're really effective. So in my lifetime, there's been a dramatic change in how we treat MS. And there's a lot of hope when people come into the clinic and they want to choose a treatment for MS, and we can usually find a treatment for just about anybody. But it's an autoimmune disease, which means our immune system, which is there to protect us from the environment and viruses, instead begins to enter the brain and spinal cord and slowly damage it. And early on, patients have acute attacks or relapses, and that's the most common kind of MS, known as relapsing, remitting multiple sclerosis. And it's there, when we look in the brain and spinal cord, that MS patients lose myelin. That is, the coating of the nerve cell is really important. It allows us to do things quickly in milliseconds or even quicker because of this coating of the nerve cell known as myelin. And early in disease, when people are having attacks, it's the myelin that's being slowly destroyed, and that's why people have symptoms. And so that dovetails with the other part of MS. So this acute part, relapsing and remitting, which affects the myelin, actually the medicines are really good at nipping that in the bud and preventing those attacks. But over time, and I see this in the clinic all the time here in Saskatchewan, is that after we quench the attacks, after we stop the attacks, people still get a little bit worse every year, or at least some do. And that's the second phase of MS, known as the progressive phase or the neurodegenerative phase. And that's where our research comes in. So instead of the myelin coating, we're actually finding underneath the myelin, the nerve cell itself is being damaged and destroyed. And that's the degenerative phase. Okay? And so as the nerve cells slowly get damaged, then people slowly lose function. And this is where our discovery came in. If you look at nerve cells under the microscope in people with MS, and we can see them and they're large. But we found in the brains of MS patients that something was abnormal, and that typically a protein, a small piece of that nerve cell, is usually in the nucleus, and that protein is known as heterogeneous nuclear ribonuclear protein A1, but we'll just call it A1 today, which is much easier. And so instead of being in the nucleus, actually in people with MS, it gets stuck in the cytoplasm. And we think as it gets stuck in the cytoplasm, and that nerve cell can no longer function normally, and it begins to slowly die. So we make this observation in people with MS, right? And we take it to the bench. We take it to the lab, and we try to model it and see if we can make the same thing occur in the lab. And by modeling it in the lab, we can now design drugs to fix it. And so we can grow nerve cells in a petri dish in the lab, and actually we can put A1 into those nerve cells, a specific kind of A1 that gets stuck in the cytoplasm. And when we do that, when we see A1 get stuck in the cytoplasm, in fact, the nerve cell slowly begins to die. So nerve cells have these really long neurites, or these long appendages, and in people, they could be as long as 3 feet, right? So the nerve cell, when you're telling your brain to move your leg, actually that's just a handful of nerve cells. The first one goes from your brain to your spinal cord, and the second one goes from your spinal cord to your leg. And so that structure beside the nerve cell is known as an axon. And when A1 gets stuck in the cytoplasm, in the lab, we can actually see those axons start to die. We can grow individual nerve cells in a petri dish in the lab and look at them, and we can measure how long their axons are and where A1 is in the cell. We can also give mice a disease that looks like MS. That's known as experimental autoimmune encephalomyelitis, or EAE for short. And we inject these mice with certain myelin proteins, and lo and behold, their legs and limbs start to get weak, their tail gets weak, they have trouble walking. And when we look under the microscope, we can see those same nerve cells beginning to die, and A1 is again stuck in the cytoplasm. And our goal is to try to coax it back into the nucleus where it belongs. And we think if we can do that, we'll save the nerve cells. We really are using some really high-tech artificial intelligence and bioinformatics, and even people at the synchrotron at the Canadian Light Source are helping with this. So we actually designed a peptide. A peptide's a mini protein. It's only about 20 amino acids. And we've designed this peptide to specifically interact with A1. And so if we think about cells and how things work, everything kind of works in 3 dimensions. And so how that protein folds, what it looks like in 3 dimensions, really determines its structure and where it goes in the cell. And so now we have A1. We think it's changed its 3-dimensional structure in the cytoplasm, and it's stuck there. And now we've designed a peptide that will interact, actually touch parts of A1, and change its 3-dimensional structure so it's more likely to go back into the nucleus. So peptides are really important, but it's hard to give people peptides. They're small, and they get eaten up by the body, and they're easily metabolized and eaten up in the body. So what we can do is, now that we have this 3-dimensional image of A1 and how this peptide is interacting with it and how it's changing its three-dimensional structure from something that likes the cytoplasm to something that's going to go in the nucleus. Now we have all that three-dimensional mathematical information, and we can take that three-dimensional structure and we can now put it into public databases. And we can ask the databases, are there any drugs that are known to mimic what the peptide is doing? And this is where the high-power computing comes in. Unfortunately, it takes longer. We just can't throw it in there overnight. It actually takes weeks and weeks and weeks. Figuring out their three dimensions is extraordinarily complex. And so you're right, we can take this three-dimensional information and put it into these databases and ask the database, is there a drug that can do the same thing? And this is in the public domain, and there's a lot of drugs in those databases that have already been invented, right? We're comparing our experiments and three-dimensional structure of A1 to things that are already available in the market. And we're trying to ask the question, what drugs will coax A1 back into the nucleus just like the peptide did? We are being as aggressive as we can because we think we're really onto something very interesting. But again, what will happen from the database is the database will probably spit out 100 possibilities, and then they'll rank them from most likely to work to least likely to work. They'll rank them numerically from best to worst. And we'll take the top 25 and bring them back into the lab. And we'll take those 25 drugs and we'll put them back in the same petri dish we had with A1, in that form of A1 that was stuck in the cytoplasm, and see if we can coax A1 back into the nucleus. So we have to get the drug in the cell, and that takes some effort. And then we can coax A1 back into the nucleus and see if we can save its axons. And that's the in vitro part. And then we're going to do the same thing with the animals and see if we can cure the animals. We are part of this whole process is try to understand, why does A1 get stuck in the cytoplasm? That can give us a clue to its three-dimensional structure. So we do experiments that kind of ask the why question. And again, we look at that peptide A1 interaction. Just takes a long time for us to figure out. We actually have to cut A1 into little pieces and see where the peptide sticks. So we need to know its location, where it sticks, and then we need to know how it sticks to the protein. So all these are ongoing in the lab every day. We hope to have preliminary data, at least a list of drugs, in a couple of years. And for this kind of work, that's a really, really aggressive timeline, and we're going to keep ourselves on that timeline. So hopefully, we're not going to have a magic drug in a couple of years, but hopefully we'll have a handful of candidates that we can really look at, make sure they work in our system, they fix A1, they're safe in people, and then we would start small clinical trials with people who have MS. It always brings me back to the patient, in that, again, the meds are really effective at the front end of the disease where there are attacks, and we can reduce those attacks with the medications. But it's when patients come to me and say, I'm dragging my leg a little more, I can't keep up mentally like I used to, and it's this kind of slow, degenerative, kind of what I call kind of nickel diming of people's function that we would really like to nip in the bud. And it would probably look like people may be on two medications, right? They would be on the medication that would stop the attacks. That's still really important, and that improves people's lives. And then we would have an add-on medication to try to prevent them from getting worse after we've stopped the attacks. We're really, really excited about it, and that we get to do, research not just in what causes MS, but we get to do research on how to treat MS. So it's a really, really exciting time here in the province.
Well, that was all quite fascinating, I thought. What did you think? Does that make sense to you at all? And are you interested in seeing where this goes? But at least it's something to chew on for a while we're waiting for all of the other developments to become available to us in the marketplace. You take good care of yourself, and I will see you again in my next video.